Okay. Hello, everyone, and welcome to IBIP's England's webinar on the missing link. To introduce myself, I'm Ranjit. I wear a number of hats for IBIP's England. I'm one of the board members and also the editor of our newsletter. And as for my profession, I worked as a consultant engineer at Design Builder. Now, before I move on to introduce our speaker, allow me to mention that if you are not a member of IPEPS England, you can become one for free, and we will keep you updated on the latest news, events, job opportunities, etc. And I will post the link later on the chat box, which you can go to and become a member. And also during the webinar, if you have any questions, please post them on the Q&A box and not the chat box. I repeat, please post any questions you may have on the Q&A box and not on the chat box. And we will try to answer as many as we can at the end. Now, to introduce our speaker, we have Annie. Annie is passionate about reducing the impact of built environment on the climate while maintaining comfortable and beautiful places to live and work. After gaining a PhD in renewable energy and architecture from University of Nottingham, she moved to USA to pursue career in industry, working for Baumann Consulting, a company based in Germany and the USA. And he headed up a team of 5 delivering building physics services, specializing in building simulation for LEED, controlling complicated and cutting-edge mechanical systems, early design optimization, thermal comfort studies, and so on. And notable projects include working with LBNL and UC Berkeley on research projects funded by ARPAe to scan a building and automate the construction of an energy model, a net zero and living building building challenge, and large-scale energy modeling in for a county in Virginia. After 8 years in the USA, and he moved back to the UK and worked in London and Bristol on commercial projects with the emphasis on modeling from conceptual design to end of life of a building, with 80% of our building stock still being used in 2050, and he wanted to have a large impact on the space and co-founded Resustain, a proptech company that automates the construction of dynamic thermal models to find control optimizations that can reduce the building's energy by 20 to 50% with no capital expenditure. With that, I'll hand over to Annie, and if you have any questions, please do post them on the Q&A box. To you, Annie.
Hello, everyone. I apologize, I can't see anything but Ranjith. So you'll have to let me know if any questions come in. But I'm here to talk to you about controls and how energy models can save the world. So I'm going to do a bit of background first, because I think it's important to always remember the background of what we're doing. And then we'll go into performance gap, or what I like to call the operations gap, the importance of those controls, and then some real life examples. I'm very much a hands-on, have to learn hands-on, practical kind of person. So that's the way we're going to move forward. Now, I just got very nicely introduced, but I'll just do a very quick sweep through of highlights. I originally did my degree in mathematics at St Andrews University, and then realised there wasn't much I could do with that in the real world, so engineering was calling. I went to Nottingham University to do my MSc and PhD in renewable energy and architecture. This is a picture of me in front of a rainwater tank on BBC Breakfast. I had nothing to do with that rainwater tank, had no idea what I was talking about, but I was there in a high-vis vest. Also, it didn't belong to me. It was good fun. I really enjoyed my time there. I then moved to the US, spent 8 years in industry there. That backpack you see me wearing there was called RapMod. It is a automation. You walk around a building and it automates the BIM and BEM models. It was an amazing project to work on, and I really enjoyed that. It was my first sort of taste of the tech industry coming together with the construction industry. And then finally, I moved back to the UK, wearing the same dress, which is always good in pictures, where I learned all about modelling in the UK. And we'll talk a bit more about that later. Now founded a company called Resustain with 5 other people to reduce carbon in buildings, essentially, all to do with existing buildings. So I think we've introduced this already, but as I think we all know, existing buildings are a key to solving the climate crisis. So 2/3 of the global building stock in 2040 exists today. Big buildings make up 5% of all buildings, but contribute to 50% of total emissions. So they clearly are very critical to deal with. Once a building is built, there are actually not many points of intervention. It feels over its lifetime. So it's really important that when we do intervene, we either intervene correctly or we have continuous intervention. And it's anticipated that embodied carbon will be responsible for the majority of carbon emissions associated with global new buildings infrastructure between now and 2030. So embodied carbon is becoming far more important than it has in the past. So existing buildings currently waste between 20 to 30% of their energy usage through operational inefficiencies. So if we can tackle that, we can really start hitting into the numbers that we're seeing above here. So I'm going to go right back to the start, and I apologize, but I think it's really important that sometimes we have to remember that we're building on top of people's work, not just starting from scratch. And actually we're building on human endeavor, not just starting from scratch. So very quickly, and I apologize for my terminology. This is my not official term. I didn't have any architecture training, so I apologize for any terminology I'm using here. That's not what that's called. So if we start, buildings have always been for the people who use them. And I think fundamentally we need to understand that buildings are for the occupants. That's their only purpose in this world, is for the occupants. And so we started just building shelter through natural materials and close by. We've got adobe structures in the US. We've got stone thatched roofs, small windows, thick walls, fires to heat them. So these were very simple structures, but the idea was to keep nature out so that we could have a comfortable environment inside. Now I'm going to talk about residential, but it's the last time I'm going to talk about it, and move on to commercial in a minute, because I'm much more interested in commercial buildings than I am residential buildings, but residential shows us the way. So we started by keeping nature out. The purpose was to keep nature out to give us a comfortable, safe place to live. We then spent more time indoors. So we needed to increase the window size. We needed to work with the building in order to keep it comfortable for us. So if we look at kind of Victorian structures, we're looking at actually using nature within the building in order to condition it, to ventilate it, to bring daylight in, and to work with what we have outside, inside, to provide a comfortable environment for the people inside. If we move, and we move, these buildings were created to have fires for heating, but eventually moved to kind of radiators and boilers to replace those fires. So technology starts to come into our buildings. And then if we come to now, we're talking highly insulated. We've got mechanical ventilation, heating and cooling for comfort in our buildings. So our buildings have become almost the opposite of natural. They are now highly technical structures. So we went from keeping nature out to using nature within the building to then keeping nature out again. So I call these 2 basic principles, and this is going to cause a lot of confusion, I'm sure, because I call one passive design, which is to use nature within the building, not to be confused with passive house, not passive house, just passive design, meaning the design works with the nature around it. And then the other one I call active design, which is nature is not allowed into this building. We are going to actively use technology within inside the building in order to condition it. We're getting to the controls, I promise. Building stock in the UK, we've got everything. We don't currently sit in, well, we do use thatched and stone wall houses as pubs and things, but tend not to use them so much for commercial. So if we look at commercial, we're talking Georgian buildings and Victorian buildings, which are based on that, using nature within them. Hospitals, Victorian hospitals, are a really good example of how we use nature within both the building and the healing process. Then we come to sort of 1960s to 1990s, where energy was cheap, carbon emissions weren't really super on anyone's minds. So we have kind of thinner envelopes, lots of technology inside for conditioning, lots of HVAC. And then we come to modern day office buildings, which have gone into that highly technological world where the facade is very highly designed, constructed to work with the HVAC inside. And they're much more complicated structures. And we're more concerned about their carbon emissions. So thought in how everything goes together is very important. So let me just talk about what I mean by letting nature in and keeping nature out. So if we look at passive design, you've got a cooling season, you've got a heating season. So the cooling season, you've got lots of shading on the windows to stop the midday sun coming in. Lower sun can come in, heat the space. You've got thermal mass to soak up the heat. You've got operable windows to allow natural ventilation in. You've got blinds to block the sun. And you've got cooling potentially from the outdoor air if it's lower than the inside air temperature. So you've got a kind of building that works side by side with nature around it. In the heating season, you've got the low sun is allowed in to heat the space up. You tend to have a ventilation system to allow to shut off the natural ventilation, bring the air in via an air handling unit, possibly with a heating coil in it. You've got perimeter heating, you've got fan coils to heat the space, also cool the space if necessary. So you've got a fairly standard building that we see and work in many, many times. In the cooling season, you allow fresh air in through the air handling unit if the windows are closed. And we use blinds to shut the light out and the heat out as well. In an active design, kind of do the opposite. You create a very thick envelope to stop any sun or heat entering the building. We have triple glazed windows, we have thick insulation. In the summer, that keeps the heat out of the building. We have highly mechanical systems. So you have an air handling unit with fans, heat exchangers, heating coil, cooling coil. You have your VRFs, so your fan coils to condition the space. And the windows, crucially, inoperable. You have external blinds, again, to stop any of nature coming in. In the winter season, you have the same thing. It basically operates in the same way, but it has heating instead of cooling. So the operation of an active design is pretty standard throughout the year, whereas a passive design building, it peaks and troughs according with nature. Okay, so why is this so important? It's because it's all about control. So we're looking at commercial buildings at this point. So are there any control issues with using passive design versus using active design, and how would that impact the building's life over the course of its lifetime? So passive design is hard to control, I would say. Nature, famously, is hard to control. So we can control it a bit, but we do have some issues potentially. If the windows are open, it might be that your thermal comfort conditioning will go on. So you have the potential of losing heating and cooling out of your building. If you have natural ventilation through operable windows, you have an uncontrolled amount of fresh air coming in, which means it might trigger the heating and cooling to go on. Heating or cooling, and heating and cooling potentially at times. You've got thin envelope, which is great for bringing heat in, but not great for holding it. Also not great for holding the cool, so the cool escapes as well. So there's various things which, unless you control the envelope and the windows very carefully, you have potentially a lot of conflicts with that and the energy usage within the building. In the heating season, similar things happen. You can potentially have ventilation air coming in too warm, which triggers the cooling in the winter. So you get conflicts, and also your light envelope allows the heat to escape. So it has a lot of benefits, but it also has some control issues, which make it very hard to make sure we're using the swing seasons, using it correctly in the swing seasons. Active design. You have your envelope which holds the heat and the cooling within the building. So what you've put in the building stays there. It doesn't escape through thermal mass or through the envelope, which gives you slightly more control, but also means you can overheat and overcool that envelope quite easily. You've got a heat exchanger, which allows the fresh air to be rewarmed as it, or cooled down, recooled as it passes through. You've got the envelope stopping the heat or the cool getting in. So active designs are much more controllable because they don't have nature basically to contend with. I do love nature, but it's not great from my point of view within the building. So there are a lot of control issues, and buildings are very, very complicated. And I think that's something that maybe we'll talk about in a while. Now, one thing that gets me a lot, and I'm sorry, and this could be very controversial, the difference between natural ventilation and natural cooling is fundamental and very, very different. I just pulled these images off. Sorry, I didn't have time to draw my own. They're not, I apologize, they're just illustrative. The purpose of natural ventilation is to remove CO2 buildup from occupied spaces, and it must occur all the time that space is occupied, so throughout the seasons. It also needs to remove moisture potentially and provide a pleasant environment for the occupants. You have to note is that all ventilation air that comes into a building has to be conditioned to provide thermal comfort. So you don't want to feel drafts, you don't want to feel cold in the winter, you don't want to feel too hot in the summer. So any ventilation air, wherever it comes from, doesn't matter where it comes from, will need to be conditioned, and energy will need to be put into it in order to make it comfortable for the occupants in that environment. So for instance, if it's winter and you're using natural ventilation, that natural ventilation is coming into the space, that cold air, it then needs to be heated up. It's also uncontrollable through operable windows. You don't know how much is going to come in, a lot more than if you've got a fan controlling it. Natural cooling is different. Natural cooling is using the air, using stack effect, using the facade in order to cool that space, not provide a release for CO2. It just happens that you can do the two things at the same time. Its purpose is to either remove heat from the space or to provide cooling to the space and provide a pleasant environment to the building. Natural cooling is very complex to make it work so that you don't conflict with a lot of other things going on. In your house, you've got one window, you can open or close it. In an office building, there's hundreds of windows and people might not be opening and closing them at the same time or doing it as is expected. For natural cooling to work, the path of the air is absolutely critical. So if you break off any part of that path at any time, so if someone closes a window, that might stop the whole system working. So natural cooling is a complex system to make work well in a building. Natural ventilation is uncontrollable air coming in that needs to be conditioned. Just making sure we do that. So what is this all about? Why don't buildings necessarily work in operation as designed? Because what we've got, we know the theory, we know the design. So I'm interested in what happens post-construction. But if we look at just what happens before construction, we understand a little bit about what happens post-construction and why it doesn't work so well. So essentially, you have lots and lots of very skilled expertise going into schematic design, REBA 1 and 2, or design development, REBA 3 and REBA 4. Masses of very skilled, very expert people designing, modeling, working together, communicating. So by the time you get to REBA 4, you have had a lot of people already in that. You've maybe switched design teams already, so even more people. So you might have had a break between 2 and 3 and 3 and 4. which might not have communicated the design completely as we go across. Sequence of operations is what I call them, because I was educated in America on them, and I can't remember what they're called in the UK. Maybe they're called sequence of operations here. But essentially the controls as how you operate your HVAC are very often copy pasted in, because we have very similar mechanical design. Not ideal. By the time we get to REBA 5 and 6, you have a whole new team on board. There's lots of VE exercises. It doesn't necessarily, the design hasn't necessarily translated, or the design intention hasn't necessarily translated all the way over here. And things might start moving away from that. Modeling is not really involved here. You might have some compliance modeling, but after that, not much. Handover, you might, if you're lucky, have a commissioning team. You might not. And your BMS will be programmed there and then, but not necessarily according to design intention and so on, because knowledge gets lost as we move through the design process. So then you hand over the building. And now what you have is one, maybe two people looking after this building. And what they have to do is keep it running, keep everyone happy, make sure that things don't break down. And often they're only there once a week on a Tuesday. So you've taken this incredibly complex design building with lots of experts involved, and you've said, here, you're very busy, but please run this building to how it should be run, and make sure everyone's happy and that nothing goes wrong. It doesn't make a lot of sense. There's not a lot of modeling done then, and buildings tend to be left alone. So we have a lot of breaks in the design process anyway, as to the design intention, how the controls work often aren't even put through, and also stating whether it's a passive design or an active design isn't really looked at, isn't really passed over either. So why does an energy model help? Well, let's start with what is an energy model, because I think it means a lot of different things to a lot of different people, and it does a lot of different things. So the most sort of basic, as we have in the UK, I would say, is a compliance model. Now, what's important to understand about a compliance model is benchmark modeling. It is not, should not be used to inform design other than for compliance, but not to inform design intention. And it also doesn't necessarily hold all the information about the design. So it certainly doesn't forecast how the building will operate in the future. It's not its purpose. Its purpose is to benchmark one building against another one, gets another one, gets another one. You then have green certification. So you have modeling involved in green certification. These have different levels of modeling. Some are very detailed, like a neighbours model that will include all of your HVAC, your schematics, your controls. Some will be slightly more basic, like your BREEAM modeling, which sometimes doesn't necessarily need those factors in them. Then you have modeling to inform design. So early design, this tends to be like shoebox modeling. So lots of parametric modeling to find the right shapes, the right way a building should be designed. Again, doesn't really forecast what's happening in operation stage, but it does help the design team understand the best choices they can make in terms of energy. And then I would say you have kind of calibration modeling. These aren't the only ones, obviously, but this is my categories. Calibration modeling, which is a fully calibrated complex model. So it includes all of the information about that building and tends to be done, well, it can only be done post-occupancy because you can't calibrate. Otherwise, you can do the detailed modeling prior to that in sort of neighbours certification type thing, or TM54. So there's lots of methodologies for that. There's lots of indications as how you should do that, and what the right way to say a model is calibrated, but that should reflect the performance of the building. So that modeling should reflect the performance of the building. Now, it's really important to have experienced that level of modeling, I think, in order to inform design, because modeling in a calibrated energy model takes a huge amount of inputs understanding, knowledge, data. And you are modeling the building as it will run. So it gives you a great understanding of how a building actually works and where things can go wrong. Because when you're fixing your model, you start finding where things can easily go wrong in real life as well. Because as you're building a model, you have to get all your envelope details, as always, all your internal gains, all your schedules, all of your HVAC equipment schematic, how they run, and all of your control points. So you have to understand all of those things in order to create this calibrated energy model. You also then need to take your monthly data, utility data or meter data, whatever you're calibrating to, and understand where the nuances have gone wrong. So this brings me to my very favorite phrase, the performance gap, which I'm going to say, when I heard about the performance gap before I came back to work in England, the performance gap was all about how modeling softwares might have slightly incorrect calculations here and what they're using assumptions here. And the performance gap was more about what the difference between the calculations are and the methodologies behind those calculations and the real usage of the building. When I came to England, the performance gap was my building doesn't work like my Part L model said it would, which obviously makes no sense because those are benchmark models. So it shouldn't be working like that. So I'm going to rename the performance gap, but we'll rename it in a minute. So what are some of the what I think are misconceptions? This is from the wider community, not necessarily the modelers but the wider community, I would say. A lot of people blame the occupants. Really easy, because occupants are really easy to blame for stuff. And there's nothing you can do about human behavior. So there's that one. Buildings are static. Once they're built, they don't need any more attention. We've put all the effort into the design phase. Once you've handed over those keys, those buildings are going to run like a dream. What could possibly go wrong? If we put a BMS in, then the building is fully controlled. And if I want to make my existing building net zero, or I want to save carbon, I'm just going to have to put a lot of money into that. And it's going to be too expensive. So I'm going to say it's not a performance gap. It's an operations gap, is what we're seeing in the UK. Or if we're using that terminology, it's an operations gap. So what we look at in the sort of traditional approach when we come to existing buildings is, right, how do we retrofit this building? We'll make a model of it. We'll decide what needs to go in, new facade, new HVAC. We'll do some parametric studies. We'll see what the best thing is. Going to need about 1 to 4 years of capital expenditure into that to get us to our new carbon pathway. But what people tend not to do is say, is this building performing as it was designed? What is wrong with it in order to fix it? So the first thing to do is look at the control inefficiencies. And this is where I call it the operations gap. This is where we're finding about 30% savings in energy. So a significant amount of savings that can delay the asset stranding by quite a few years just by reducing that energy usage, which means that not only have you reduced the energy usage, you've found where the issues are with the building. So what you might have thought was a facade issue actually isn't a facade issue, it's a lighting issue, or it's a cooling issue, I don't know. But what might have been the preconception without looking at the operations gap isn't necessarily correct. So you can shrink that operations gap. You can then delay the stranding of the asset. You can have more time to think about how the money is spent and actually spend much less money on creating that net zero building. So that's my context. I'm going to go into some case studies now to sort of show you all how this works. The first one is a sort of straightforward case study of sort of what we've done. And then the other two are going to be a bit more sort of precise issues and why controls are so critical to a building. Okay. So The methodology for this case study was that we would connect into the BMS, stream that BMS data onto a platform, translate it, create a calibrated digital twin using BMS data and using utility bills, and then find the control optimizations. We run those optimizations through the digital twin, the calibrated model, to provide a forecast of what savings might be possible. And then you start activating the measures and realigning the building according to the optimizations that we find. So this building is a 1960s building. It has a partial HVAC retrofit. It still has the air handling units that were installed in the 1960s, which unfortunately isn't very unusual, although they've been going strong, so good for them. Less embodied energy. So this is what we found. This is some of the data that we found. So we've got the air handling unit fan is continuously on, and our supply air temperature is all over the place between 36 degrees and 18 degrees. So we've got really mixed information of the BMS. So then, I mean, I'm sure if you're on this ABIPSA webinar, you know how to create an energy model, but let's go through it very quickly anyway. These are the envelope properties. We found them through a site visit, basically, pictures and so on. These are the zoning of the building with the internal gains, watts per meter squared. The one thing you'll see is the scheduling. The scheduling isn't on-off. We use the ARPAe schedules, which are very, very good. They're definitely in Appendix G of 90.1. I say definitely, maybe they're a 90.1 appendix. But you can find them, and they are very good way of modeling buildings. Then we looked at the HVAC. And this is normally in the UK, I found, where a lot of the modelling stopped. But this, I think, is the most interesting part of it all. So I hope people will model this more. So essentially, you build out the air handling unit. So in this case, the original air handling unit was a VAV system. And it had boilers, chillers, cooling towers. It had reheat coils in each of the 4 risers going down the building, north, south, east, west, to release the air. And then it had dampers on each floor. Had a return duct, and then out into the world. So this was retrofit. What they did was they decommissioned the cooling part of the VAV system and fitted VRFs into each of the tenant spaces. A very typical retrofit, I would say, in the UK is VRFs being retrofitted into tenant spaces is great, but also very typical. But what they didn't do is then look at the changes that needed to happen within the air handling unit in order to support those VRFs and make sure that all the spaces were comfortable. So what we found, we have various points on the graph. So you've got your return air temperature and your return air fan. So we found that there was quite a lot of air going back into the mixing box, as it were, the plant room. And the temperatures were higher than maybe we thought. So maybe slightly higher than 24, 26, sometimes 27. And then you've got your fresh air coming in. The fresh air was, they needed 13,780 litres for removing the CO2 from the building for the occupants. It was actually coming through at around, not quite 37. It was designed for 37. I think it was coming through at around 25, 26. So a lot of air coming in that was mixed. We actually found that the outdoor air damper was what do you call it? Open. Fixed open. So all of that was outdoor air coming in. Then we got our boilers at 70 degrees, fairly standard temperature, hot water temperature. Our heating coil in the air handling unit was coming off at about 12 degrees. So it wasn't really doing much in that in the air handling unit, and then the reheat coils were set to 32 degrees. But what was really interesting about those is that their valves were actually sort of stuck open. As I said, this is a 50-year-old system, so not that surprising. So some of that air was coming in at 40, 45 degree temperature. So then the VRFs had to work with those kind of temperatures coming in at them. So we found quite a lot of conflicts already. This is all the information about the equipment. So we went and found all the equipment, made sure it was all modeled correctly. So we modeled it, all the curves. We looked up all the makes, the model numbers, made sure they were modeled as they should be. So not just a single flat line, as it were. The boiler curve was modeled, the fan curves were modeled. Those were all in, and then we calibrated. We used the IPMVP methodology, although I think methodology is in that acronym, so I don't really know how to say it. No, maybe it isn't. Anyway, you can see here the results of that. What was most interesting for us was we could now break down where the energy was being used in the building. That's really useful. So the model is now giving us much more information than the metered data and the BMS data is. And now we know we've got that model, we can start playing around with it to see how we can make it better. So we took the data from the model, because the model gives us every point we could ever want: temperature, flow rate, so on. So we looked at how the energy was flowing, or how the air and the temperature was flowing through the air. So at winter, you can see the outdoor air comes in at sort of 6 degrees. You've got return air at 25 degrees. It mixes. So we've got a VAV system. It comes to about, I don't know, 12 degrees, let's say, goes through the fan, picks up a tiny bit of heat there. Then it goes into those reheat coils, goes up to 32, and there's put into the spaces, and the the VRF doesn't go on. Great, nice and warming, perfect. Then we have the same in the summer, did the same in the summer. So the outdoor air was at just under 20. The return air was at about 25. Mixed came to about 22, let's say. Adds a little bit of heat on through the fan. Very flat, nothing's going on. And then the VRFs are cooling to comfort for each of the spaces. So summer and winter, great. What happens in the swing seasons? In the swing seasons, we've got the air coming in at around about 14 degrees, return air at 25, mixes to about 16, goes across, that heating coil doesn't do anything. The reheat coil is now on, takes it up to nearly 30 degrees. That goes into the spaces, and the VRFs go on to cool it. The VRFs cool it to 10 degrees when the outdoor temperature was about 13. So all of that energy is wasted. Could just be a nice straight line. So what we saw here was that these reheat coils were using a ton of energy. This is the annual energy usage over the year. So these reheat coils were using a ton of energy, and the cooling coils were also using quite a lot of energy. So we wanted to look at how we could mitigate that. So here's a bit more of the sort of calibration, I don't know, information about the building. So this is the metered data. Then if you put it back to the original VAV with reheat, it would have used about 10% more energy than it does now. So good retrofit, save 10% of energy over all that time. This is it running now. Now, if we limit the fresh air to only 10 litres per person, then in the model, we can sell 12% of the energy. If we put the air handling unit to supply air temperature to 18 degrees, we can go to 26% of the energy. And then, because I'm a big heat exchanger fan, if we put a heat exchanger into the building, you can go down to about 33% of the energy. So these two things can be done via controls. This would be a retrofit item. So what we did, we started optimizing. So we put the fans on a schedule, occupancy schedule, and we put the supply air temperature at a steady temperature, not at 28 degrees. I would just like to add. So here you can see what happens. So this is the calibrated model prior to optimization. And this is, I think, the calibrate. Yeah, so this is the calibrated model after optimization. Same here. This is electricity. This is gas. So you can see it's fairly well controlled in the model. A couple of hiccups maybe as we first began, but it's not bad. It's not a bad calibration. Now, what we can do to see how much impact the control changes have had is that we can use the calibrated model and take those control changes off and run it through for the weather data of that time with what's going on in the building, and then we can see what impact those control changes have had. So you can see here for the electricity, not much. We weren't really hitting the electricity. What we were hitting was the gas usage. As you see, we dropped the fresh air down and we dropped the temperature of those reheat coils down. And as you can see, the gas usage decreased significantly once we went into optimization over those winter months. So we've been in there for a year. We've been in there for over a year now, but we've been in there for a year, and savings for that year just through control optimizations. And this is realigning the building over every quarter for the seasonal adjustments, but then also checking regularly if any of the control points have gone off. Someone's changed the temperature here, someone's switched the fan off or whatever. We can put those back into the correct optimal positions. Overall, 28% of the energy was saved, so actually not too bad against the forecast, which is nice. Pleasing. Fundamentally, though, 232 tons of carbon were not emitted into the atmosphere, which is, for this building, 65 kilowatt hours per meter squared, which is more energy use than a net zero building would use. So does that mean we can build a full net zero building to account for all those carbon losses? I don't know, but we're looking at, just through control optimizations, about a 30% saving, and that's all through the digital twin being able to, or the energy model being able to understand the building in that detail that we need. So I've got two more for you. I'll be very quick on these ones. This one had no FM on site. So what was interesting about this, it's a classic, what I would call a DOAS, a fresh air only system with VRF for conditioning, very popular. It has a heating coil, which is gas fed, but or hot water fed, but mostly electric. The stranding date here when we got there was 2031. Again, we did the analysis through the HVAC system. And what we noticed was that the thermal wheel was being bypassed in the swing seasons when it shouldn't have been, and that the air handling unit was providing 25 degrees supply air temperature, which was activating the cooling on the VRFs, which you'll see here. So we predicted we could find a 46% saving on this one, which would move the stranding date to 2038. So that gives 7 years of time to move that building into a net zero pathway, as opposed to an extra 7 years. So this is what happened. Essentially, we started our control optimizations. We produced the savings report for it. We went to Edinburgh to physically work on the BMS. What we found, though, was that the heat exchanger logic wasn't programmed correctly. So we hadn't looked into that in enough detail. We just made our change, and actually we found out it wasn't programmed correctly. The air handling units went under refurbishment, so that stopped control. And then also it wasn't clear what we were doing, and so some of our work was bypassed and reset. But overall, after 10 months, we got 68 tons of carbon saving at 35% energy savings. There's the optimizations, running short on time. I'm not going to say much. Again, looking through each control point, we can do that via the model, which is good. Then we compared it with weather. So we looked at the weather to see how it affected the usage from 2022 to 2023, because everyone likes to compare year on year. It just doesn't work. But then we sort of showed why our forecast was different from what was happening in the year, because we forecast off 2022 and we activated in 2023, and then where we couldn't didn't find quite the right control logic. Same with electricity. Those are the carbon savings. You can see that they're fairly consistent. As we've gone on, they've got lower and lower, which is nice to see. So we've understood the building better. The model keeps calibrating with it. Understand more and more as you're calibrating the model where the control issues are. As costs. So we got to there. If you see that the total saves 68 tons of carbon, it's almost £30,000 in operational energy costs, which is a significant amount. And again, 58.5 kilowatt hours per meter squared. So we're looking at a whole net zero building's energy being saved just through control optimisations. The stranding date is currently at 2034. So this is the one I just want to go through again very quickly. This was a net zero retrofit. And this is what I think is the most interesting. I'm interested. I don't know. So we calibrated, you can see it. It was an all-electric building. It was a dedicated outdoor air system with heat exchangers, VRF units for comfort. A fantastic retrofit. All made sense, well planned, great. Now, if you look at what I found really interesting was how quickly this building fell out of control. So it went in operation in May, a little jump in energy there, but I'm not surprised. First month, I'm sure there were some tweaks. Gradually, uses more energy up. And then by the 2nd May, you start to see there's a significant amount more energy being used in the same months of the years of the next year. And this can't just be weather, because it's 30%, 35% more energy. So it can't just be weather. So when you look at the calibration, we could calibrate the model, the striped lines of utility, the solid calibration of the model. You can calibrate the model to show, yeah, we understand how this building is being controlled. We're close. The calibration is never quite, if you've got it exactly, there's a problem. But we sort of understand where our bits work and don't work. But what you start to see is when the building starts to diverge significantly. So it's diverged by May, but actually if you look further back from that, you can start seeing that it was actually October, really. October, so 1, 2, 3, 4, 5, 6 months in, the building started to diverge from its control optimizations, from its optimal control points. And that's after 6 months, the building stops operating optimally, which I thought was fascinating. So, and it's nobody's fault. I always have to say this is just, someone changes something over here, or you mend something over there, the controls just start going off. No one's looking at them. It's no one's job to keep these buildings aligned, to ensure the optimization or they're operating optimally. It's a very skilled job to understand how they are operating optimally. And no one really has the time. There's a lot of other things to be done. So it's just fascinating to see how quickly it does slip out of control. So you can see here essentially the green is how the building should be operating, and the grey is how it was operating. So, or how it would have been operating had the controls not been on. So here you see again, it's November, December, it starts really falling out of line. And you can only see that through a model, because you have to use the calibrated model in order to either predict out or estimate how it would have improved if you put the control optimizations in. So here you can see that we're looking at 40 to 50% savings month on month through the control optimizations. And you can see those are from heating and fans. So this is the air handling unit, heating and fans. So you start seeing 56% savings, 60. You start seeing these huge drops in the central ventilation. And then you can see, and I would like to point out, the scales are incredibly different, 180,000 to 20,000. But you can start seeing how the VRF units are affected on each floor by the air handling unit being adjusted. So you can start seeing in January, we were about 14,000. By the next January, down to 12,000. They're starting to reduce the amount of heating that they do as well. So the results so far on that one, we're looking at 101 tons of carbon saved, which is fantastic, 37% of energy. The EUI has gone from 97, which was already pretty good, which is why no one was noticing the slip out control, down to 76. Hope to get it down to 55, which is where we want it to perform as a net zero building. And then the things we found out along the way is that various things were missed over time. So the runaround coil didn't have fluid added to it, so it's never been working. Some of the systems weren't connected up to the BMS. There's a lot of strange VRF controls going on. Some of them are on 24 hours a day at 16 degrees, conditioning space 16 degrees. And so with the full set of BMS data over a year, you can start nuancing those controls even further as we go. So, conclusions. We waste between 20 to 6% of energy through poor control. It's not the easiest place. That's not true. It takes, you have to know what you're doing, but it doesn't involve CapEx. And it's really important to get those buildings working as they should before putting the retrofit in. It's so important, because otherwise you just end up spending a lot of money and the same mistakes are being made anyway. I would say bespoke modeling is really important. Calibrated modeling, it lets you understand how the building is operating and you can find those root causes of the issues. Keep continuously calibrating the model. Then you can work out the more nuanced control issues that you're seeing. It's a data management issue. So automation is key here. You've got a lot of data. You need to crunch it fast and make sure that you've got it under control. And controls require no CapEx, no embodied energy, and lots of greenhouse gas savings or carbon savings. So we can save the world. That's it.